So let's measure Young's modulus for a nickel-chrome alloy wire, a wire of nichrome. First thing we're going to want to do is know the diameter of this wire. So I'm going to use a micrometer and I'm going to measure the diameter of this wire in a few places. Let's close it with the... Oh, first of all, let's check for zero error. Zero error of that is negative 0.01. Better make a note of that. Zero error. And I'll have to make sure I subtract the zero error from every measurement. Right, now open up the gap between the spindle and the anvil using the thimble, and then close it again using the ratchet. .43 millimeters. Let's make some more measurements. There, that's my measurements done. Okay, let's calculate the mean, calculate the uncertainty, and then we can subtract the zero error from the measurement. The mean diameter, 0.439 millimeters. Fine, let's subtract the zero error, and I've got the diameter there. So what we've done here is to get the uncertainty, we've taken the maximum value, 0.45, subtracted the minimum value, 0.43, that gives you 0.02, divided by 2, get 0.01, expressing that to two significant figures, and then making sure the decimal points match, decimal places match, which is why I had that extra significant figure there. Right, that's the diameter done. Let's move on. We're going to need all sorts of equipment for this because we're going to lay the wire horizontally across the bench top, and we're going to use as long a bench as possible. These jockey wheels have a hole in them, and for some reason some students thread the wire through that hole. But then the wire isn't lying horizontal and it's dragging against this edge here, so ignore that hole. We don't need to use that. And we make sure this is clamped firmly on the edge of the bench. On the other side of the bench, I'm going to tie the wire onto this, which I've clamped in place. It shouldn't be able to move very much. It's certainly not enough to affect the results in any way. Some people clamp the wire, but then the wire can slip through the clamp. So what we're going to do is tie it instead. Now, there are advantages and disadvantages to tying the wire in this way. The disadvantage is over this particular length, we've actually got two wires, but also this bit is going to be a weak point. Now we can tie this tighter to here so that the uncertainty in that length is less and we haven't got two wires there. Or we could measure the original length from here and place a fiducial marker to make sure that this point doesn't move enough in any measurable way. And that's just what I'm going to do. I'm going to place a fiducial marker here and check it doesn't move. If it moves a little bit, I can adjust the measurement accordingly. One of the ways the experiment fails to get good results is that the wire must be free from kinks. And if we have a look down the wire to see how free from kinks it is, you can see it's not especially free from kinks. As we follow down this wire, there's a kink very obviously there. Big kink there, lots of kink there, look at that. This is a very kinky wire. So not expecting much of these results, but never mind. On the end we've got our mass suspended. Now this shouldn't be enough mass to cause permanent deformation of the nickel-chrome wire. I've just put that there to try to keep it nice and straight. And how will we make fiducial marks? Well, we've got a bit of tape here, haven't we? So let's just put this tape at the end here. And another piece of tape on the desk. Now these are quite a long way away from each other, so this isn't ideal. Actually, instead, we could use a clamp stand. In fact, we can use anything as a fiducial marker, but I'm going to use a clamp stand, and I'm going to position it so that this tape is just touching the clamp stand. Now, if that tape moves, because this bit at the beginning extends by any amount that is measurable, I will be able to measure it and then take that into account. That's good enough at that end. Now we're going to measure the original length from there, from where the fiducial marker is at that end, to some point all the way over here, as far away as we can. So the original length will go from all the way over here to down about there somewhere. I've prepared in advance a homemade vernier scale. Rather than using a travelling microscope, because most schools don't have class sets of travelling microscopes, perhaps some do. We certainly don't. So I've prepared this vernier. I might use a guillotine to cut that more straightly. Just cut it roughly for now. That'll do. Now the plan is to stick this part, and I've cut it right to the edge of the scale, to stick this part on the wire and mount this part so that it doesn't move relative to the desk. Actually, we don't even need to use this bit because it's just a ruler. I could use another ruler. But there we see we have our vernier scale. So as the part that moves, the part that's on the wire, extends in this direction, we'll be able to measure the extension to 0.1 millimeter resolution. There we are. I've managed to get it mounted. I'm just using the ruler. You can see the 9 on the main scale lines up with the edge. The wire is going to extend that way. So I've got to be a bit clever when I read from this scale. But there we go. That way I'll be able to measure the extension very carefully using this vernier. Scales weren't quite lined up in the vertical plane, so I put a little book under it just to bring them closer. Not quite lined up. Look, could do with just a little bit more elevation on the main scale. We are finally found a use for these formula sheets. Just getting it just right so the scale looks good and the effect of parallax is minimized. Good. Right, we can start taking measurements, I guess. Now I need to measure the natural length, the original length of the wire, from there all the way down to there. That's longer than a meter, so there's going to be some uncertainties associated with this. Let's go get a meter stick. Okay. Oh, I'm sorry you had to see that. So the original length of the wire in meters is 2.04. I can't measure it any more accurately than that. And how much uncertainty? Well, there was 1 millimeter uncertainty for the first measurement and the second and the third. So that is plus or minus 0.003. That's 3 millimeters of uncertainty. Oh dear, they don't match. So let's pop another little 0 in there. There we go. So in meters, 2.040 meters with a very conservative estimate of 0.003 meters as the absolute uncertainty. I wonder whether I should be a bit more liberal with that. Let's go with 2.040 plus or minus 0.006 instead. I've doubled the absolute uncertainty because I'm not convinced it was very well measured. Let's say a millimeter in each reading rather than a millimeter for each measurement that I took. That would be 0.006 meters uncertainty in the whole measurement. So let's go with that. I feel better with that. Okay, let's add some mass and measure the extension. This is what my table is going to look like. Let's do the measurement. Oops. Now, up to now, I've been a bit relaxed with safety. I haven't been thinking about it. But actually, I've got a wire under some tension here, and it could snap or a knot could come loose. So there's two things I should do. First thing is stop the wire whipping back, and I can do that by placing a metal yoke over the wire. That's just going to mean that if the wire snaps and whips back, that's going to stop it from flying up too far. Second thing is I should put these horrible things on. Should have done it from the start. They're on now. I've taken a few readings, and I've got quite a bit of mass hanging from the end there. And of course, our vernier shows that we've got a few millimeters of extension. There's my results now. It's probably enough. I don't need it to snap, so let's do some analysis. There's our table. I can add a caption to the table, but I don't think I need one because I think it's clear enough. So I am actually just going to plot my graph. Now, I just think about what I'm going to plot. Our equation for Young's modulus is stress divided by strain, tensile stress divided by tensile strain. So that's equal to the force divided by the cross-sectional area, and then all of that divided by the extension, which I'm going to call delta L, divided by the original length, which I'm going to call L. Now, the original length I've got. The cross-sectional area I can calculate from the corrected diameter. But the force is the mass multiplied by g, the gravitational field strength, the mass that I have added. And delta L is the extension. So m over delta L. Now, if I plot m on the y-axis and delta L on the x-axis, then the gradient will be m over delta L. That'll be that figure. That will be the gradient. So m over delta L being the gradient would be equal to E A over G L. So that's if I plot m versus L, m versus the extension. That's what the gradient will be equal to. And we know what A is, and we know what G is, and we know what E is. So I can calculate what that is. So I don't need to calculate the force or the stress. I don't need to calculate the strain and then plot stress versus strain to get the Young's modulus as the gradient. I could get the gradient of this, and then E will equal that gradient multiplied by GL over A. And that's when m on the y-axis and delta L on the x-axis. Okay, so I've got all that information, and when I'm thinking out loud, this is the sort of thing that I am writing. I'm sort of writing this down so I know what I'm going to be doing. I don't care about y-intercepts, although that will tell me if there's a systematic error. I do need to calculate what A is, or I could just put it into this equation, because we're going to assume that the wire has a cylindrical shape. So the area is going to be 2 pi r. Pi r squared. Gosh, that was embarrassing. Pi r squared, or 1/4 pi d squared. Okay, so pi r squared or 1/4 pi d squared, the 4 goes up there because it's the denominator of a denominator. Right, we've got d, there it is. We've got L, there it is. We've got G, 9.81. Gradient we need to get. So let's plot this graph. I've chosen my scale, so my data points, which go from 0 to 1800, will occupy more than half of the available paper. And from about 1, what was the extension going from? 1 to 3.8. So 1 to 3.8 is just about, just a little bit more than half the available paper. So that seems like a sensible scale. Let's get the points plotted. There we go. Now, unsurprisingly, we seem to have more extension, or the extension here that we get for a given increase in mass seems to be greater. But that's because the wire was straightening out. Let me get this bit here that looks pretty straight. Now, I think that bit there, it looks pretty straight. That is going to be where we want to calculate our Young's modulus, that straight bit there, because the wire, if I use this bit down here, that's still the wire straightening. So I'm going to ignore that curved bit at the beginning, and I'm going to draw my best fit line like that. Now, it doesn't go through the origin, but that's okay, because we already had the wire loaded with mass to try to straighten it up. So I don't think that's a massive problem. Let's calculate the gradient of this line. Now what I'm looking for is two places on the line. I'm going to indicate them with dots where it passes nicely through grid lines so that I can get decent, easy to read numbers. And let's write those coordinates down. There we go. Those numbers are written down, so now I can calculate my gradient from those. But I do have to be careful of the units. Let's just do it. There we are. Now I've calculated it. The units of this are going to be grams per millimetre. Interesting units, so we're going to have to do something with them in a bit. But don't worry about that right now. Let's go back to this calculation here and calculate what the Young's modulus is in whatever crazy units this gives us. We can fix the units later. So there's the calculation written out. You'll notice I've included the units so I can strip them out now. So let's separate those units out. There we go. Now let's work out what the conversion... Actually, let's do this number first, and then we'll work out the conversion factor to get it into a sensible unit of gigapascals. So let's first of all calculate that answer. Right, obvious nonsense units. So let's fix that unit. That's a little bit on the high side, doesn't it? In gigapascals, we've ended up with 1.10428 times 10 to the 3, 4, 5 gigapascals. So that seems to be at least 2, maybe 3 orders of magnitude too big. Let us go a-googling, as they say. Young's modulus of nichrome wire. That's what that comes out as. Of course I accept it. Nichrome. Is it all nichrome then? Nichrome, nickel alloys, blah, 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 blah. Property, where's bulk modulus? There it is. Minimum value, maximum value. Yeah, we are like 3 orders of magnitude away. Should be somewhere around there. Let's check our unit conversion, because 110 would have been perfect if there was a power of 10 error. So let's check our unit conversion again. Yes, I missed one. My unit conversion was incorrect. So here, I cancelled the grams with the grams, no problem. And I saw the kilo and put 10 to the 3. But I missed the milli part. There's a 10 to the negative 3 there as well. Then there's the newtons, and there's the... It's on the denominator, so milli becomes 10 to the 3, and it's squared. There it is. And that's the meters squared. So I missed in this conversion that milli. There's a 10 to the negative 3 there. They cancel. That becomes not 10 to the 9, but 10 to the 6. And that becomes not 10 to the 5, but 10 to the 2. There we go. I missed a milli. And I'm glad I did, because I could see the results were obviously wrong. That's why we looked them up. So what I can do now is I can reference the fact that the minimum value is 110, and I got 110.4 gigapascals. I am right on the money for this website. So let's reference this website. And there we are. That is referenced as well as it needs to be referenced to A-level. Expected value is that according to that full URL accessed on that date and at that time. That is my reference. And there is the value that I got. Now, I do need to do an error analysis. So let's look at this graph again and think, well, what's the worst gradient that would possibly be acceptable? Well, if we use all our data points, it'll be around about there-ish. Of course, you wouldn't use that line. You'd never dream of using that line, but that's the worst acceptable line of best fit. Let's label the other one LOBF for line of best fit, and this one worst acceptable line of best fit, or WALOBF. There we go. Now let's measure the gradient of that. There's a point down here that I want to use on my graph, And there's a point up here I want to use. Let's use that one. Same method as before. Recorded the data point, that's 1520 there. Recorded the data points, calculate the gradient, and there it is. Now, that's the worst acceptable line of best fit, so the difference between them, that would be the uncertainty in the gradient. Wow, two significant figures. It's 45% uncertainty. What I did is calculated the absolute uncertainty in the gradient and then divided it by the true value of the gradient, this value from up here, this one, and that gave me the percentage uncertainty in the gradient. Now, if I want to work out the percentage uncertainty in Young's modulus, what I have to do is add together the percentage uncertainty in the gradient to the percentage uncertainty in the original length to the percentage, 2 times the percentage uncertainty in the diameter, because the diameter is squared. And that would give me the percentage uncertainty in my Young's modulus. I know it's going to be really high, but let's go through the motions. The percentage uncertainty in the original length is 0.006 divided by 2.040, which gives me 0.29%. 0.29% as the percentage uncertainty in the original length. Barely worth considering, certainly not worth considering in this calculation, plus 2 lots of the percentage uncertainty in the diameter, which is 0.01 divided by 0.449. So that's 2.2%. Percentage uncertainty D is 2.2%. That's probably worth including. 2.2%. Now I add all those together. So 45 add 0.29 add 2 lots of 2.2 gives us 49.69%. Call it 50% uncertainty, which we can then multiply by this value. So let's get that as a, well, let's leave it as 50%. So our value of E, which was measured E, is equal to 110. I'll worry about the decimal in a second. Let's do 0.5 multiplied by 110428, just to see what comes out. 55. We only want 2 significant figures, so there's no point including the other decimal places here. Plus or minus 55 gigapascals. There it is. And we can see that the value of the expected is within that range. So we could write a very basic conclusion. Just something like that. Measured Young's modulus of nichrome agrees with accepted value within experimental error. And that's it. Now, the whole thing has taken me an hour. Of course, we didn't see all the various measurements and stuff because I kept pausing the video. But that's how long it took to do it. It doesn't take that much in calculation. You can lay this out a bit better, maybe explain what these labels mean, add some captions. You don't need to do any more than this. So let's look for the evidence then. Well, if I was given the written instructions that I followed, that would be evidence for competency 1. If I didn't, then really I'd want to have some sort of remark about what my control variables were, how I was controlling them, you know, the experimental procedure. I'm trying to make sure there's no kinks in the wire, making sure I was very careful to check that the the end of the wire that was nearest the wall didn't move, or at least didn't move by any measurable amount. We might want to talk about the dependent variable, how we were making accurate measurements using the vernier scale, all that sort of thing, making sure we're using the instruments properly, using the micrometer correctly, taking our repeats, all that sort of thing can fall into competency 2. Competency 3 for safety, I wore goggles. Now, I might have failed competency 3 because I only thought of that part way through. The wire wasn't under a tremendous amount of tension when I remembered, and it wasn't really at risk of snapping until I remembered. But still, that was a bit shaky. I should have failed competency 3 on that. Competency 4, I'm consistent. My decimal places of my numbers matches the resolution of my instruments. The titles are right. The tables are clearly laid out correctly. I've made all the observations that I needed to make and used those, so that's all fine. Competency 5, I've processed the data using appropriate tools, that is to say a graph, including error analysis of the results. Yes, I made a mistake, but you're allowed to make mistakes. I spotted it, and I knew it was a mistake because I looked it up and I referenced the correct value properly, and so I have met the requirements for competency 5. So that would be, in this case of 1, 2, 3 pages, and a conversation. Don't look at that. And a conversation with the person who's assessing me. That would be enough, I think, to pass this particular required practical. Hope you enjoyed it.